Okay, guys, here we go. So a little bit of backstory on photoelectron spectroscopy. And I think I mentioned this to you previously. But guys, when I first learned about this in 2013 in preparation for the changes that came on the 2014 AP exam, I and most of my colleagues gathered in a theater-sized room, all raised our hands when we found out about the new material on the new curriculum on the test, when they said, and one of the things you're going to see is photoelectron spectroscopy, and we all went, we have no idea what that is. And this is a room of people with bachelor's degrees, at least, in chemistry. Honestly, my initial response to this was resistance, because it just felt like somebody was pushing an agenda, and they were. But as I got into this, what I found was it's actually fascinating. The science, the chemistry behind what PES is and why it works is actually really cool. And I think you're going to find it interesting to learn. So guys, what we're going to do is we're going to kind of fill our mental toolbox here really quickly. This is actually the first 2 pages of the slides that I gave you. And so what we're going to do is we're going to talk a little bit about the forces that electrons see. And you'll notice that I put the word see in quotation marks. We'll talk more about what that means in a minute. Then guys, we're going to introduce a new unit of energy. You've heard of calories. You've heard of joules, but what you'll find, especially if you if you move forward in particle physics, is you'll find that we typically, physicists and many times chemists, don't think in joules and calories. They think in terms of what are called electron volts. It's just another unit of energy. We're not going to talk about what it means, other than for you to understand that it's a unit of energy that applies specifically to things with charge. And we'll get in, and we're just going to define that quickly. And then, guys, what we're going to do is we're going to start to talk about the chemistry behind PES. And as we do, we're going to put an equation on the board that you'll never be asked to write or solve. But what you're going to find is the equation is a really good way to understand how PES works. As we go into that, guys, what you're going to see is that it's going to start to sound familiar. Do you remember when we answered, I think it was question 35 in the homework, and we talked about this idea that if we add energy to an electron, any additional energy goes to accelerate the electron, and that's kinetic energy? That's what this is all about, and we're going to come back to that, and it's going to start to sound a little familiar. And then, guys, frankly, what we're going to do to wrap up the day is give you the only thing that I have relative to homework for this. Your book has absolutely no problems in it relative to PES. There's very little in terms of support relative to what we can talk about with PES. So frankly, what I did is I created my own assignment, and it's going to make you nervous because you're going to look at this and you're going to go, that can't possibly be what I'm going to be tested on. What do we need to know for the test that'll then be on Tuesday? And guys, the answer is simply going to be, trust me. The test that you're going to take on Tuesday, the questions that you will see on the test will come completely in alignment with what we're going to do today. And frankly, it won't be free response. It'll only be multiple choice. Then what you'll see is on the practice exams that we'll start taking in April, you will see free response questions over PES on the 2 released exams that I've got access to, but I don't want to show those to you now because I want to be able to use them later as we're practicing for the real test. Does all that make sense? Okay. So guys, with that said, let's jump into this and let's talk about some background understanding. So guys, you've got this atom in front of you, right? And we all understand that this is the nucleus. And guys, be selective and don't write nucleus in the circle because we're going to draw all sorts of stuff. Write in pencil. You're going to be erasing a lot. Do you guys, any of you need pencils? You need an eraser? Anyone else? Oh, yeah. Oh. Who has one like it? Did you steal that from me? Yeah, because I finally had to restock. No, yeah, well, because of last year, people kept stealing them. They're good pencils. You can't have nice stuff in this school because people steal it. Have I told you about those letters? Oh, no. They don't want to make it right. They just, yeah, no. Oh, yeah, they just want to confess so they can go on their missions. All right, so, guys, here's what we're going to do. We are going to use this atom, and you guys understand the arcs are actually the energy levels, right? We're going to use this atom to represent many different atoms. First hydrogen, then a helium ion, then a helium atom, and then a lithium atom. So technically, we only need the first two energy levels, but I just wrote them all to just give you a sense of scale, not scale, but what we're talking about. But guys, as we go through this, what we're going to do is we are going to have a conversation about the forces that these electrons see. Guys, and please feel free to use this terminology when you're writing on the test, although you won't be writing this on the test because it'll only be multiple choice. But when you see free response questions about this, feel free to use that terminology of C. Physicists and chemists love to talk about the forces that particles see. And what they're really talking about is the forces that they experience or that push and pull on them. But guys, we talk about that as being seen. So what forces do these things see? So with that out in the open, let's get going. So guys, first of all, let's make this a hydrogen atom. Go ahead and do that with me. I think what you can do is if you write down the letter P positive for proton, then you'll just be erasing the numbers as we go from hydrogen to helium to lithium. Okay, so what we're going to do then, guys, is let's make this into a hydrogen atom. So, looking at a hydrogen atom, and of course we don't need these other energy levels, but they're just there for reference. So guys, looking at a hydrogen atom, what force does that electron see in a hydrogen atom? We see an attractive force from that one proton. Does that electron see any repulsive forces? It does not. It only sees an attractive force, and that attractive force is a product of the nucleus pulling on it, positives and negatives. Does that make sense? Okay. So guys, there's a name for that. That is what is called a Coulomb Bec attraction. It's not a question, it's not a term you'll be tested on, but guys, we may as well just call it what it is. Coulomb Bec refers to the attractions between positives, oh wait, you ready for this, Catherine? Yeah. Positives and negatives. That's Spanish. Huh? There you go. So guys, Coulomb Bec refers to the attraction between positives and negatives. So the Coulomb Bec attraction that this electron experiences is simply the attraction of the nucleus. Now, guys, can we quantify that Coulomb Bec attraction? How? No. Yeah, how about negative R sub H divided by N squared? Right? See, guys, that equation allows us to quantify that force of attraction. And remember we had the conversation that explains why it's negative? Because that negative value tells us that it is an attraction relative to a fixed point. And as we move away from that fixed point, I guess I should go this way. As we move away from that fixed point, the nucleus, we end up becoming less negative to a maximum of 0, which means no attraction. So guys, we already know how to quantify this Coulomb Bec force through the Rydberg equation. We doing good? No, so this equation only works for hydrogen. But do we have equations that describe this in more complicated atoms? Absolutely. We just don't need to do it. Is that okay? Okay. All right, so guys, are you settled with what we're saying up until now or questions? We're building foundation. You're good? Okay. So now, guys, do this with me. Change the 1 to a 2. Just erase the 1 and make it a 2. So, and you'll notice I wrote helium below this, although technically right now what this is a helium ion, right? Okay, so now let's have the same conversation. What just happened, and let's use our words, what just happened to the Coulomb Bec attraction that that electron sees if this is now a helium ion? Oh, it did, and in fact it did, it doubled, but you just need to know it went up. So guys, the Coulomb Bec attraction that this electron sees went up. It did in fact double, but don't worry, you just need to know higher. So guys, here's the question. Don't miss this idea. How will that change the behavior of this electron? Good. One thing it does is it gets closer. Physically, a helium ion is smaller than a hydrogen atom. Stop and let that sink in. A helium ion is smaller than a hydrogen atom. Go ahead. We're not going to go there. But it is very electronegative, yes. But don't worry about that right now. Okay, so guys, are you okay with that idea that it's smaller? Now what about this? How do we do this? So, okay, so negative r sub h divided by n squared, and I'm not going to ask you to do the math, but if we came up with some value, negative x joules, for the energy of the first energy level, again, that's for hydrogen. What would that value be for helium? Greater or less? A helium ion, greater or less? No, just, well, yeah, absolute value. Would it be more or less energy? More energy. So what does that mean? And guys, maybe I should pause. Hold on a second. What does that mean? So if the energy of the electron goes up, just a minute. If the energy of the electron goes up, functionally, what does that mean? Well, it means we would have to add more energy to that electron to get it to jump out of the atom. Pause there for a minute, because guys, that's critical. So we're talking about this 1s electron, okay? And if we go back to a hydrogen atom, so this is one proton, we can figure out how much energy it takes to get rid of that electron, because that's equal to the energy the electron possesses, which is given by this equation. So if we add that much energy, the electron's going to go away. Is that okay? Okay, now, what if we're now back to this, and it is now a helium ion? Well, guys, if this is a helium ion, this electron is more tightly bound because the nucleus is stronger, so we've got to add more energy to that electron to make it go. Does that make sense? Okay, so let's do questions so long as they're on point. We okay? Okay, so now, guys, let's do this. Let's change this now to a helium atom. Add your other electron. So now, guys, the question is this. How much energy will... Ooh. I wasn't in drawing mode. There we go. Okay. So, guys, how much energy will it take to remove this electron relative to hydrogen? More, because we have a stronger nucleus. Guys, how much energy will it take to remove electron 2 compared to electron 1? The same. They're in the same energy level. They experience an attraction from the same nucleus, so the amount of energy that's required to remove these electrons will be the same. Go ahead.
Why is it that electrons in the same energy level don't?
Why don't they what? Why don't they repel each other?
Yeah,
they do. No, they do. But understand that repulsion, if you will, so there is a repulsion here. And we don't draw it that. I mean, really, these should be separated. And again, this is all treating electrons like particles, but it's okay. So there is a repulsion between these electrons, but it doesn't change the attractive force that both of these electrons see from the nucleus, because that repulsive force is coming from the same plane, if you will. Does that make sense?
Yeah,
So,
and that one's like
exactly, and you're going to find out that that's not true when we go to lithium. So guys, are we okay with this idea in helium that these two electrons in helium will require the same amount of energy to remove them because they're in the same energy level? Go ahead.
it's still smaller than hydrogen.
And it is greater than hydrogen.
Once you add that electron.
Oh yeah, absolutely. So yeah, I'm so glad you asked that, because that's critical. So guys, if we could do this, and I don't think you need to do this in your notes, but if we could go back and if we could then compare this to hydrogen, so if we could find out the energy that's required to kick that electron out of hydrogen, which is given by negative R sub h divided by n squared, if we know that energy, then this energy, the amount of energy required to remove either one of those electrons, is greater than the amount of energy needed to remove that, because the nucleus in helium is stronger. And those go hand in hand, right? The smaller the size, the more tightly bound the electron, the harder it is to remove. Guys, remember that, and it's really cool that Gwen's brain went there a little while ago. She started thinking electronegativity. And do you remember that principle that we learned about electronegativity that said smaller is stronger? We applied it to electronegativity. It applies here as well, because what makes the atoms smaller? Well, a stronger nucleus. And so those same strong, small atoms that are good electron taker-inners, electronegativity, are also really good at hanging on to their electrons, which is what we're talking about now. Go ahead.
Okay, so I get those two things, but I'm
Mhm.
wondering, the helium ion,
Okay.
is the helium mole atom the amount of energy?
Yeah, good question. So let me draw for you what I think you're saying. So what about this? Helium ion, right? So are you asking, what is the comparison between removing this electron and that electron? We're going to call them the same. For our purposes, with what we need to do, we're going to say the amount of energy to remove an electron from a helium ion is the same as the amount of energy to remove an electron from a helium atom. Both of them are greater than hydrogen, but for our purposes, we're going to say they're the same. They are a little bit different because, as Matt got us thinking, technically there is a little repulsion between these two electrons, but it doesn't play into what we're going to do with this. Okay, because actually the other reason they're a little bit different is because these two electrons with opposite spins, their spin energies actually interfere with each other as well. We don't need to understand it at that fine of a level, though. Go ahead.
So you showed the equation as the negative RH over n
Uh-huh,
squared.
yep.
But aren't they in the same n sub for the helium and hydrogen? So how about the energy?
No,
Negative
yeah,
RH
because,
works for hydrogen.
yeah, the negative R sub h divided by n squared does not work for helium. Yeah, that only works for hydrogen. You guys, are we good? Okay, now guys, track this, because look, I think you can probably guess where we're going next. Let's go to lithium. And guys, let's just jump right to lithium atom. So now that we're talking about lithium atom, let's now talk about the forces that these electrons are seeing. And let's use, Catherine, the term that you brought up a second ago. So guys, these electrons right here, these are what are called core electrons. If that doesn't make sense, or if you can't keep track of that, you may want to write it down. So guys, these are core electrons. What is true of the Coulomb Bec attraction that these two first energy electrons see in lithium as compared to helium? So are these electrons more tightly bound in helium or in lithium? Tighter in which one? Lithium. Guys, these two electrons right here, These two electrons are more tightly bound in lithium than they are in helium. Why? Because lithium's got 3 protons. And these 3 protons have a greater Coulomb Bec attraction for all electrons, but especially these electrons right here. Does that make sense? Okay, now let's do this. Let's talk about this guy right here. Let's have this conversation first. What forces does that electron see? Good, and that's what we've got to add to this. Because guys, does this electron see a Coulomb Bec attraction from the nucleus? Absolutely. But guys, that's not the only force in town now. Because now this electron sees the repulsive Coulomb Bec force of the core electrons. And Daniel used the term, but if you're not familiar with this, and I know it's in your notes, this is called shielding. So guys, shielding is the repulsion of the core electrons as it interacts with the valence electrons. So now, this electron, oops, oh wow, that was cool. This electron right here is now seeing an additional force. Yes, it does see the attraction of the nucleus, but it also sees the shielding of the inner core electrons. Just a second. So now guys, let's compare this. Let's compare this to hydrogen. Hydrogen and lithium both have 1 valence electron. Do you agree? Hydrogen and lithium both have 1 valence electron. Which one's going to be harder to remove? The electron in helium or the electron in hydrogen? Or I'm sorry, stop. The electron in hydrogen or the electron in lithium? 1 or 2? Which one's harder to remove? 1. Hold on, no, just listen guys, this is critical. This electron in hydrogen is more tightly bound than this electron in lithium. Let's talk about why. So guys, we understand that lithium's got a stronger nucleus, right? So a stronger nucleus, 3 protons, we might think would bind the outer electron in lithium stronger than the outer electron over here in hydrogen. But guys, it turns out that's not the case. Why is it that the lithium electron is easier to remove? The shielding. Guys, physically, this valence electron is further away from the nucleus. And guys, you all understand that attraction decreases with distance. So guys, not only is this electron further away, but it is also shielded by these inner core electrons, and consequently that valence electron in lithium is easier to remove than the valence electron in hydrogen. It's critical you understand that. So what questions do you have? Go ahead. So shielding is the repulsion that the valence electrons experience as the core electrons push on them. And more and more and more. So if you had an atom that was all the way out to here, then this electron would be shielded by all these electrons. No, they shield so they're all shielding one another, but practically the thing that we talk about is how all that shielding affects the outer electrons. Because for now, those are the ones we're talking about removing. Just a second, go ahead.
So, how strong is the shielding of electrons compared to the attraction?
Yeah, good. So what is the relative relationship between the attraction of protons and the repulsion of electrons? And that's actually the next thing in the notes. This is actually what you're asking is, you're asking about something called effective nuclear charge. So guys, let's talk about this. You may see this on the AP test. So effective nuclear charge, and I'm going to give you the equation for it, although they'll never ask you to really solve this. But guys, what does the word effective mean? Well, it means what effect is it having? So let's again talk about this electron. So what forces is it seeing? It's seeing the attraction of the nucleus, and it's seeing the repulsion of the inner core electrons. And so, and guys, think about this with me, effectively, the overall attraction that this electron is seeing is the attraction of the protons minus the repulsion of the core electrons. Does that make sense? So guys, there's actually an equation for this. You'll never have to solve it, but it's actually this. No, sort of. Minus number of electrons minus 1. So guys, this is actually the way that you calculate the effective nuclear charge. So it's the atomic number. Well, actually, that's not true. Sorry. It's this. Let me see if I can undo this, because that doesn't work in this system. So it's Z minus core E. So functionally, what's happening is, and don't ever think about it this way, but mentally you could think that every core electron cancels a nuclear proton. But guys, you'll never, if you Google this, this is what you'll see. If you Google effective nuclear charge, Wikipedia will feed you this equation. You'll never be asked to solve it. But what you do need to do is be able to conceptualize the idea that the overall or effective charge that this electron sees is the number of protons pulling minus the number of electrons pushing. Go ahead.
Doesn't it have to take into account the fact that the electrons are closer to the valence electrons than the protons?
It doesn't. What you're saying is true, but it doesn't have to take that into account. We just need to know that the attraction that electron sees is the pull of the nucleus minus the push of the inner core electrons. We can really just leave it at that. Go ahead.
So if you do that equation with the lithium, then isn't it just like blood?
Mm-hmm.
And then that's the same as the hydrogen, so isn't it just the distance?
Exactly. Then it becomes a function of distance. Yep. Okay, you guys okay? Okay, so now guys, do this with me. We're going to transition. Ethan, head up. Here we go. So guys, now what we need to do is now that we understand this idea of forces that are being seen, we now need to talk about this new unit of energy. So guys, when you see this on the test, you will not hear about attractions in joules. You'll hear about these attractions in what are called electron volts. And guys, an electron volt is a unit of energy that many times scientists will use to talk about the energy of charged particles. That's all. You just need to know it's a unit of energy. But guys, it can be converted to joules. You'll notice that this is a very small, you don't need to know this, but it can be directly converted to joules. So an electron volt is a very small fraction of a joule. Okay? So let's put this in context. So what are some things that we can talk about to get a relative sense of electron volts? Well, guys, first of all, this, and it's actually, again, interesting, Gwen brought this up, electronegativity, an atom's ability to pull in electrons. Well, guys, fluorine, and what do you remember about the electronegativity or affinity of fluorine? Highest on the chart, right? Guys, fluorine has an electron affinity of around 3.4 electron volts. I know that that's vague, but the idea is, so when we talk about an element that's really good at pulling on electrons, we're talking about a force of about 3.4 electron volts. So now let's talk about some bonds. And we understand that bonds are attractions between positives and negatives, so we can measure their strengths in electron volts as well. Hydrogen, actually, so the bond in hydrogen is actually, diatomic hydrogen, is actually stronger than fluorine's attraction for electrons, 4.5 electron volts. This one's interesting. Diatomic nitrogen. Guys, diatomic nitrogen's strength in electron volts is actually almost 10 electron volts. Here's the thing that's weird. That's the strongest bond in nature. That's the strongest bond anywhere. Guys, the strongest bond that exists, we could say the universe, the strongest bond that exists is the bond that exists in diatomic nitrogen. Why would it be so strong? Triple bond. It's a triple bond, and nitrogen is amazingly small. There are other elements that do triple bond, but nitrogen is the smallest, and therefore this is the strongest bond. So are you starting to get a sense of this? So now, guys, don't miss this one, because this is interesting. Now let's talk about the attractive force. We've got the attractive force for fluorine for other electrons, hydrogen for other hydrogens, nitrogens for other nitrogens. Let's go back to the previous conversation. What about the attraction of hydrogen for its electron? And guys, it's this. It is stronger than the strongest bond that exists in nature. So this, what we just threw up on the board, guys, what we're talking about is this. It's the amount of energy with which the electron in hydrogen is bound to the nucleus. 13.6 electron volts. It gives you a relative sense of how hard that electron is bound. You get the idea? Because now, do you understand this? I just need you to know that you understand this. Okay, so now guys, watch, because this is an interesting transition. As we switch slides, let's go back to this. So guys, now what we're going to do, now that we understand a little bit about electron volts, we are now going to start assigning energies to energy levels in electron volts. But before we do, let's make sure we remember how to do that in joules. So we'll go joules on top, and we'll go electron volts on the bottom. So guys, how do we figure out the energy of an energy level in joules? In hydrogen. Oh, kiddos, negative R sub H divided by N squared, right? All right. So let's just throw up the number for energy level 1. So when you plug the Rydberg constant in, you end up with this. Now guys, here's the thing that's interesting. You don't need to do this, but what I want to do is I want to convert this number into electron volts. So, looking at our previous slide, I know that 1.6 times 10 to the negative 19th joules is 1 electron volt. So a simple dimensional analysis calculation will give me this number in electron volts. And guys, I've already done the math, and the answer is this. Do you see it? Go back to the previous slide. Guys, make that make sense. Do you see it? What's magic about that number? It's the ionization energy for hydrogen that you saw in the previous table. Does that make sense? Why does that work? And guys, the idea is this. This number, whether it's in joules or whether it's in electron volts, is the energy of the first energy level, which is also then the amount of energy we've got to add to kick that electron out. Are you comfortable with the idea? Because if you are, we're going to transition. So guys, let's do questions specific to this, and if you're feeling comfortable, we'll move forward. That's the result of this plugging in 1 for n. Got it? Go ahead. This is all, well, no. So we only have the ability to do this math for hydrogen. We can't, but other people can do this math for every element on the periodic table. But we can only arrive at this number and then whatever it is for each of these energy levels. We can only arrive at those for hydrogen because that's all the Rydberg equation is good for. If we knew these numbers, we could convert them all to electron volts, but we can only do that math for hydrogen. Guys, did you understand Catherine's question? Because this may create confusion. Please hear this. She said, wait, can't we only do this math for hydrogen? And the answer is yes. But that said, we can talk about relative attractions for all the elements. So we understand that that's attraction for hydrogen, right? We can talk about the attraction for helium with 2 protons. We just know it's more. We're not going to quantify it, but we know that it's more. And then if we go to lithium, we know that this is even more and this is less. We're not going to quantify it, but we know that it's more and less. And that's where this conversation is going in just a moment. Go ahead.
So it's negative RH over n, which is the orbital square.
And well, not the orbital, the energy level, but yes.
Okay, so like the orbitals, like as you get further from the nucleus, they get more scrunched together.
Correct. Exponentially, that's what the squared does. Yes. Because you're dividing by numbers. Remember, it's in the numerator, so you're dividing by numbers that are ever expanding exponentially, which makes the difference between them always smaller.
So this isn't the equation that's like giving the joules of attraction. This isn't the equation that's giving the joules of attraction over distance, because that's.
We've never done joules of attraction over distance. We've done joules of attraction, which is relative to the energy level, but that attraction does tell us distance. So the greater the attraction, the shorter the distance. Okay. You guys okay?
Yeah.
All right, so guys, here we go. We're about to do some PES. You've got all the notes in front of you, thank goodness, because you guys are so caught up in writing stuff down that you would never get through this if we didn't. But here's the deal, guys. What we are talking about is PES. So what does PES do? It creates things called photoelectrons. Photoelectrons are electrons that are ejected from a substance due to energy that is added in the form of photons. So physically, what you do to do PES is you take a sample and you blast it with light or some other type of radiant energy. Frankly, most of the time they use X-rays. But you take a sample of an element or a compound and you blast it with radiant energy, and we know that light and all these other radiant energies are made of photons, and these photons smash into that substance and send electrons flying out. That's fundamentally what we're doing, and these electrons that get kicked out due to the addition of energy are what are called photoelectrons. Now guys, in order to understand this process, you need to understand the term electron binding energy. This is the amount of energy with which an electron is bound. Now check this out. Is this in the notes? Okay, we'll just do it this way. So guys, electron binding energy is the amount of energy required for an electron to overcome its attractive force. And guys, you may want to write this down. What do we call that attractive force? Effective nuclear charge. So we talked about this idea of effective nuclear charge, which is the strength with which the electron is bound, and electron binding energy is the amount of energy that we've got to hit an electron with for it to break free and go. But guys, fundamentally what we can do is we can think of electron binding energy as basically being ionization energy. It's the same as ionization energy. It's simply that thing that we've been talking about all along, which is the amount of energy we've got to add to make the electron go away. We're just going to call it electron binding energy because that's the term they choose for PES. You okay? All right. So guys, this is the equation that you'll never be asked to solve. But you don't need to. It's in your notes. You guys are so tied to taking notes. So guys, let's define our terms and then we'll talk about what this means. So HV looks familiar, right? What is equal to HV? Energy of what? Photons, of light. We talked about it in the context of light. But guys, this is the descriptor of the amount of energy that light possesses, Planck's constant and frequency. But what are we doing with that light in PES? Well, we're nailing a substance with it. This is simply our way of transferring energy into a substance. So how much energy are we transferring? Well, we can figure that out by knowing Planck's constant, which is constant, and then the frequency of that energy. This is then equal to EBE plus KE. What is EBE? That is the energy needed to eject the electron binding energy, ionization energy. But now guys, what is KE? That is kinetic energy, right? And kinetic energy, do you guys remember the equation? So guys, kinetic energy is 1/2 mv squared. Now and you may want to write this down with me, it's not in your notes, but guys, kinetic energy is 1/2 mv squared. What is m? Of what? An electron. That doesn't change. So what does change? The velocity. So guys, the greater the kinetic energy that this ejected electron has, the greater its velocity. So let's pull this together in an oversimplified example. So here we go. What's our element? Hydrogen. So guys, let's label this thing. This is energy level 1. This is energy level infinity. In electron volts, what is the energy of energy level 1? Negative 13.6 eV. I think this is in my notes, and I'm thinking I forgot to make it negative. I did. So let me fix it. Okay, so guys, this is the energy of this energy level, and it's negative 13.6 electron volts. So if we want to kick that electron out of hydrogen, what do we have to do? We got to have 13.6 electron volts. So here's what we're going to do. We're going to take this sample of hydrogen, and we're going to blast it with X-rays. But guys, what we're going to do is we are going to blast this with photons that have an energy of 15 electron volts. You may want to write this down with me. Now, how does PES work? And guys, everything that I write down, you're going to want to write down with me. Here's what you do. You put an electron detector, which apparently I can't spell. You put an electron detector over here. I pray that you understand that you know this isn't drawn to scale. That electron detector is not the size of an atom. Okay? And then what you do is you measure this distance D. And again, I pray that you understand that that is not to scale. Physically, what you've got, if you were doing this experiment, physically what you've got is you would have a tube of hydrogen gas, and then some distance away, you would have your electron detector, and that guy's over here, and this could be meters away, but you've got a sample of hydrogen atoms, and then you've got a detector over here. Again, it's not drawn to scale. But with that said, moving back over here, the idea then is this. We are going to blast these hydrogen atoms with 15 electron volt photons. So how does the science work? Well, guys, these 15 electron volt photons get absorbed by the atom. What part of the atom absorbs the energy? The electrons. And these electrons go, woohoo! I'm going to do it in blue. These electrons, oh, what did that do? Oh, here we go. These electrons absorb this energy. Oh, baby. What is, oh, here we go. Here we go. So guys, these electrons absorb this energy. How much energy does it take to get this electron out of the atom? Yep, 13.6 electron volts. How many electron volts did we add via the photon? 15 electron volts. So how many electron volts of energy are unaccounted for? 1.4. So guys, what do these additional 1.4 electron volts of energy do? They accelerate the electron, and then that electron flies over to the detector, and we detect the electron. No. Does the science make sense? Now let's talk about what this would actually look like. Ready? If you were actually doing this science, and don't change your picture, just watch. If you were actually doing this experiment, here's what you would see. Here's your detector, right? Here's your electron detector. And what you would do is this. You would pulse this sample with a 15 electron volt photon. And then, well, you would know this distance, and then you would have a timer. So you would go bzz, and you would hit this hydrogen with a 15 electron volt photon, and then you would measure the time that it takes the electron to hit the detector. Let that sink in. You pulse the sample with, in this case, 15 electron volt photons, and then you time the time that it takes for the electron to get to the detector. What does this do? Well, guys, the thinking goes like this. Kinetic energy is equal to 1/2 mv squared. But velocity is distance divided by time, right? We've measured the distance. We've measured the time. If we can plug that in, we know the mass of electrons. What can we solve for? Kinetic energy. And when we do that, guess what the kinetic energy is going to be equal to? 1.4 electron volts. What does that now tell us? It tells us this. Here's why. We know the energy that went in. 15 electron volts. We know the kinetic energy of the electron because we measured the distance and the time. That's 1.4 electron volts, and I'm going to get sloppy with signs. And so if we take this and subtract this, the difference is the electron binding energy. That then tells us the energy of the energy level. Let's say that again. You know the energy that went in. You know how long it takes the electron to come flying out. You know the distance. From that information, you can calculate the kinetic energy of the electron. If you also know the energy that you put in, and the difference between the energy that you put in and the kinetic energy that comes out is the energy that was necessary to strip the electron from the atom, which then tells us the energy of the energy level, where that electron came from. Does the science and the math make sense? What questions do you have? Go ahead.
I have two.
Okay.
The first is D. I understand the engine is the detector, but like, is it measuring from the electron? And like,
Well, so it depends on how good you want to get. Frankly, they typically just measure, these systems are calibrated, and you put in a fixed size tube, then that distance has already been measured. It's typically from the, so Matt's question was, where do they measure the distance from? And the answer is from the point where they know the X-rays are hitting. Does that make sense? Because they can focus those X-rays into a very tight beam. And where that tight beam encounters the sample is where the electrons, defines where the atoms are that are ejecting electrons, and that's the distance they measure.
Yeah, and then my other question was, so in theory, if you were to put, if you were to shoot a photon of exactly 13.6 electron volts, the electron would break free, but then it'd be like,
Yeah, we don't need to worry about it. In theory, it would stall, but that doesn't matter. Yeah, go ahead. Yeah. The which? Oh no, this is the mass of an electron, which is a constant. Oh, we can look it up. Wait, it's 9.11 times 10 to the negative 27th kilograms. Why do I know that? My mind is full of worthless information. We do know the mass of an electron. Okay. Yeah, and guys, but please understand, you're never going to do this calculation. You're never going to do this calculation. You just need to understand the concepts. All right. So guys, where is this then headed? What do you got to be able to do with this? Well, guys, this is then the progression of thinking. Use this as a spot check to make sure you're okay. So how does PES work? Well, this is the idea. If you can add sufficient energy in the form of photons, HV, and you can use these to bombard an atom, these electrons can actually be ejected, and guys, this is crazy, from any energy level. These photoelectrons, I'm sorry, these photons, X-ray photons typically, have so much energy that they don't just kick out valence electrons, they can kick electrons out of any energy level in the substance, in the atom, even core electrons. So guys, using PES, we hit it with so much energy that even core electrons can come out. So, each of these atoms will only eject, however, one electron. But every electron that comes out has an equal chance of being ejected. So, the idea is then this. In a large enough sample of identical atoms, you're going to have electrons that come out of every possible energy level. So the idea is that if you've got, let's do this. Let's go 3 protons, and let's say we've got lithium. If you take lithium and if you hit it with these X-ray photons, some are going to release this electron, some are going to release this electron, some are going to release that electron. Only one each, but it could be any one of these 3 electrons. So maybe we should talk about this then. What are we going to see then over here at the detector? We're going to see different times and therefore different energies. Guys, check this out. This is actually important. What you're going to see is this. You are going to see some electrons that are moving faster, and you're going to see some electrons that are moving slower. Which ones will be the fast electrons? The valence electrons or the core electrons? The valence electrons will be the fast electrons because they're less tightly bound. They're going to come screaming out, and then you're going to get some slower electrons that are coming out of the core. So these will be your fast guys, and these will be your slow guys. But, and guys, don't miss this, will you have the same number of electrons?
Yes.
No. You will have twice as many slow ones as fast ones. Don't miss this. You'll get twice as many slow ones as fast ones because there's twice as many of these electrons as those. Okay? All right. So guys, moving along then as we get into this, what we're going to find out is that these electrons that come out of the same energy level will have the same kinetic energy, but that energy will not be the same for electrons that come out of other energy levels. So guys, I think we're at the point where we can now start drawing pictures. So this data then leads to what are called photoelectron spectra. And this is what they look like. Let me show you. Guys, this is a and switch pages with me. This is a photoelectron spectra. This is what you've got to be able to do. This is it. This is how you're going to be tested on this for the AP test. They are going to either show you or have you draw photoelectron spectra. So guys, these are the things you're going to see. The y-axis is relative number of electrons. The x-axis is the electron binding energy in electron volts. Now guys, for the first 2 years, the AP authors fought over this, and we finally have an answer. High energies will be on the left, 0 will be on the right. So, they could do something like this. They could give you this PES spectra. It's not in your notes, right? Draw it in. They could give you this PES spectra. And they could ask you this question. What element is this? So let's talk about what we're looking at. So guys, how many different energy levels do we have electrons coming out of? 2. 1 and 2. Now, do these 2 energy levels contain the same number of electrons? No. This one's got 2 times more than this one. Now, which one of these is more tightly bound? The one on the left or the one on the right? The one on the left is more tightly bound because it took a larger amount of energy to pull the electrons off. So we can then do something like that, like this. We've got 1 electron on the outside of this atom that is relatively weakly bound, and then we've got 2 electrons, because the peak is twice as high, we've got 2 electrons that are more tightly bound. So thinking about the way that we draw atoms, we've got 2 tightly bound electrons, that would be these, and then we've got 1 less tightly bound electron like this, and what would that be? Lithium. This is a lithium atom. All they do is bind. So now guys, do this. Draw beryllium, element number 4, above this. So, well, yeah, so let's pretend like you're starting your graph over. So now sort of draw it up here. Guys, draw beryllium. Draw what the PES spectra for beryllium would be. It's pretty abstract stuff, right? You ready? You know what? I'm going to draw it on the same line, just so you see the. Forgive my. This should be the same height as this one. But guys, that's beryllium. Notice what you're seeing. First of all, guys, second peak is now twice as high. Why? Because there's electrons in the outer shell of beryllium. But you'll also notice that the peaks for beryllium relative to lithium have all shifted to the left. Why is that true? Because there's one more proton in the nucleus, more tightly binding all of the electrons in that atom. They're all more tightly bound. So now guys, do this. Do boron. Number 5. So I'm going to rewrite my beryllium. You guys ready for beryllium? No? All right. Well, it'll follow the trend. So guys, beryllium will go like this. in blue. The important or tricky bit is this. What does that peak represent? Not valence, the p sublevel. You've got an electron in beryllium that is a p sublevel electron that's in the, well, and maybe, hold on. Yeah, no, because the S's as well. Let me sort of, I think I may have not drawn that very well to scale. So those are more tightly bound. These are more tightly bound. And then you've got one more that's slightly more energy. So now we've got 1s, 2s, 2p.
How do you know that it's
Because it's slightly higher energy, and that's why it fills after. That's why the S fills before the P. Is that okay?
Wait, the P is higher energy?
Then the S, yeah. The 2p is higher. That's why the 2p fills after the 2s.
Here we go.
All right, guys, so you ready? This is your homework. You're going to draw the PES spectra for hydrogen through neon on the same graph using different colors. It's up to you. Here, let me just show you what I did. I went like this. How you choose to do it is up to you. But I did this. I drew them separate lines. But if you want to draw them all together, that's fine too. So let me save this, clear this, pull this down.